Hey everyone, and welcome. Today we're going to pull back the curtain on something you probably use every day but maybe don't think about, the secret backbone of your fiber internet.
All right, let's just jump right in with a big question. Have you ever really stopped to think about it? How can one single, tiny, hair-thin strand of glass deliver blazing fast internet to your house and your neighbor's house and the house down the street all at the same time? It kind of feels like it shouldn't be possible, right?
Well, it turns out it's not magic, but it is really clever. The secret is this surprisingly elegant and super efficient technology. And the cool part is, at its heart, it's actually pretty simple in its design.
So, before we get to the solution, we've got to understand the problem. So let's start with that, the challenge of getting one fiber connection to many, many homes. Okay, put yourself in the shoes of an internet service provider, an ISP, for a second. You've just laid this huge, powerful fiber optic cable into a new neighborhood. Great, but now what? You can't run a separate fiber line to every single house. That would be insanely expensive. The real puzzle here is, how do you split up that massive fire hose of data among all your customers in a way that's affordable and doesn't slow everyone's connection down to a crawl?
And that is where our hero technology steps in. So let's get into it. The solution is something called a passive optical network, or PON for short.
So yeah, PON, passive optical network. And the most important word in that whole phrase is passive. What does that mean? It means the little boxes out in your neighborhood that actually split the signal, they don't need any power, no electricity at all. It's this one-to-many setup that is just genius because it's simple, it's super reliable, and it's way cheaper to run.
So this whole system really just has three main parts. You've got the OLT, the optical line terminal. Think of that as the brain located back at the ISP's main office. Then you have the passive splitter. This is the unpowered workhorse, the unsung hero, probably in a box on a pole somewhere in your neighborhood that splits the light signal. And finally, you have the ONT, the optical network terminal. That's the little box in your house that turns those light signals back into the Wi-Fi and internet we all know and love.
This technology isn't exactly new. It's actually been evolving for quite a while. If you go back to the mid-90s, the very first versions of PON could only do about 155 megabits per second. But then around 2001, things got serious with the development of something called GPON. That stands for Gigabit Capable PON, and that is what really paved the way for the super fast internet that so many of us have in our homes today.
Okay, so we know the main components, but how does the data actually get from them to you, and from you back out to the world? It's a two-way street, so let's break down how that works. This part is honestly pretty cool. Remember, it's all happening on a single strand of fiber. So how do you talk and listen at the same time without it becoming a mess? Well, they use two totally different methods. For data coming downstream, that's to you, the OLT is kind of like a radio station. It just broadcasts all the data for everyone on your street out to everyone. But the box in your house, your ONT, is smart. It knows to ignore everyone else's data and only grabs the packets that have your specific address on them. Now, for data going upstream, from you back to the internet, it's completely different. It's like a super strict, perfectly managed conference call. Every single ONT is given a tiny, precise time slot when it's allowed to talk. This system is called TDMA, or Time Division Multiple Access, and it's how they make sure everyone gets a turn to speak without talking over each other and causing data collisions.
So you might be asking, how do they manage both of those things on one tiny fiber? The magic trick here is called Wavelength Division Multiplexing, or WDM, and it's simpler than it sounds. Basically, they use different colors of light to carry different signals. Think of it like having separate lanes on a highway, but for light, all traveling down the same piece of glass without ever crashing into each other. And here's exactly how that works. The system gives each job its own specific color of light. For example, the light coming to you with your internet and voice data uses a 1490 nanometer wavelength. If you also get TV from your provider, that might come down on a totally separate 1550 nanometer wavelength. And then, when you send something out, an email, a search query, your upstream data travels back on its own private wavelength, 1310 nanometers. It's a really clean and clever way to keep all that traffic separated and flowing perfectly.
All right, that's the theory. But what does this look like for an engineer who's actually setting up a new customer? Let's take a quick peek behind the curtain and see how it's done.
It's definitely not as simple as just plugging in a cable. There's a whole logical process. First, the engineer has to define the services. They do this by creating separate virtual lanes called VLANs to keep your internet, voice, and TV traffic from getting mixed up. Next, they have to create bandwidth profiles, basically setting the upload and download speeds that you're paying for. Then they have to set up templates for the specific equipment that's being installed in your house. And the very last step is to authorize your new device, your ONT, on the main system and apply all of those profiles and rules to it.
And here's a really simple example of what those settings might look like. You can see how each service gets its own unique VLAN ID, like a special lane number, to keep everything separate. And check out the bandwidth profiles. Notice that Voice over IP gets an assured amount of bandwidth. That's to make sure your phone calls are always crystal clear. Meanwhile, internet and TV might just get a maximum speed.
And this is what that actually looks like for the engineer. They're not typing in code, they're using a management system like this one. This is the software where they take all those rules and profiles we just talked about and assign them to your account. With just a few clicks, they can turn all those abstract settings into a live, working internet connection.
Okay, we have definitely gone through a lot of the technical details. So let's zoom out for a second and talk about the big picture. Why is this technology so important? So what's the bottom line here? The big takeaway is that PON totally changed the game for deploying fiber internet. Because those splitters out in the field are passive, they don't need power, the whole system is way more cost-effective. There's just less expensive, powered gear out there that can break. That simpler design also makes it much more reliable. Plus, it's super easy to scale up. You can just add more customers by adding more splitters. And it does all this while delivering what they call the triple play: data, voice, and video, all over that one little fiber optic cable.
So, at the end of the day, this simple, elegant, passive technology is the real reason that gigabit internet became affordable enough to reach millions and millions of homes. Which leaves us with one final thing to think about. Our hunger for data isn't slowing down, right? So what comes next? What's the next big innovation that's going to take us from 1 gigabit speeds to making 10 gigabit speeds the new normal in all of our homes?